Hey everyone, and welcome. Today, we're going to pull back the curtain on a piece of technology that honestly runs just about everything you do online. We're talking about the Database Management System, or DBMS. We're going to cover the absolute core concepts you need to get your head around if you're starting a journey with data. So let's dive right in. So let me start with a question for you. Think about it for a second. Your bank, your favorite video game, even your local grocery store. I mean, what could they possibly have in common? They seem like totally different worlds, right? But they all share one critical behind-the-scenes secret. And there it is. They all run on powerful databases. Every single bank transaction, every item in your character's inventory, every barcode that gets scanned, it's all just data. And here's the thing, as the amount of data in the world just completely explodes, the challenge of wrangling all of it becomes a massive, massive problem. So how do you even begin to handle all this information? Well, in the early days, you might think, oh, I'll just use a bunch of simple text files. But as your data starts to grow, you run into huge problems, and you run into them fast. And that leads you to a fundamental choice. Are you going to stick with simple files, or do you need a dedicated system? And this comparison really just gets right to the heart of it. Using simple files, which you see on the left, it just becomes a tangled mess. It's terrible for large amounts of data. Trying to change the structure is a complete nightmare. And security? Yeah, that's pretty much an afterthought. A DBMS, on the other hand, is built from the ground up to solve these exact problems. It's all about structure, security, and efficiency. And this is where our hero steps in. The Database Management System. You gotta think of it as more than just a box you stuff data into. It's a really sophisticated engine designed to manage all that data effectively, securely, and at a massive scale. And you know, this stuff isn't new. This technology has been evolving for decades, from punch cards way back in the 60s to the relational databases of the 80s, which were a total game changer. But look at what happens in the 2000s. The boom in e-commerce and social media created a kind of messy, unstructured data at a scale no one had ever seen before. And that directly led to the rise of NoSQL databases, which were built for flexibility and that kind of insane scale. This chart really drives that point home. It's tracking the different data models over time. You see that big chunk in the middle, the relational empire? For decades, that was the standard. But then new models, like NoSQL and graph databases, started to pop up to handle all these different kinds of new data challenges. The technology just keeps adapting. So how in the world does a DBMS actually organize all this information? It's not just a random pile of data thrown into a folder. No, it relies on a very, very powerful concept to make sense of all the complexity. And that big idea is abstraction. It's a core principle in all of computer science, really. The whole goal is to hide the messy, super complicated details of how data is physically stored on a disk and just show the user or the programmer only what they need to see. It's all about simplicity. Now, to pull off this abstraction trick, a DBMS uses 3 distinct levels, which you can see right here. I love the analogy of a skyscraper. You have the view level, that's what you see from the fancy penthouse suite. Then there's the logical level, that's the architect's master blueprint. And finally, the physical level, that's the concrete foundation buried deep underground. So let's break those down. So here's the crucial thing to get. At the very top, you've got the view level. That's what you, the user, actually interact with. It's a simplified, maybe even a custom view of the data. Right below that is the logical level. This is the master blueprint that defines all the data and how it all relates to each other. And way down at the bottom, you have the physical level. This is the nitty-gritty, the low-level details of files and disk drives that, frankly, we just don't want to have to worry about. This brings us to 2 other words you are going to hear all the time, schema and instance. And the best analogy is right here on the screen. The schema is the blueprint. It defines the structure, the rules. The instance is the actual building, filled with people and furniture. It's the live data, snapshotted at one specific moment in time. Put another way, the schema is like the type of a variable, while the instance is its actual value. Okay, let's make this real with an example. See the top part? That's the customer's schema. It's just defining the columns, name, customer ID, account number, that kind of thing. That's the structure. Then, look below. That's the customer instance. That's the actual data, Pawan, Ankit, and Nandini. That's the data as it exists right now. So, schema is the design, instance is the reality. All right, so we've got our structure, we have our data, but now what? How do we actually interact with it? How do we create that schema in the first place or ask for the data that's inside? We can't just, talk to it in plain English. We need a special language. And these languages really break down into two main jobs. First up, you have DDL, the data definition language. Think of this as your construction crew. You use commands like create table to actually build the structure of the database. Then you have DML, the data manipulation language. This is what you use to interact with the data inside that structure, to find it, to add new data, or to change it. And look, when we talk about these database languages, there's one name that just dominates the entire conversation: SQL, or Structured Query Language. It's the standard, the de facto way we communicate with most relational databases. It's got both DDL and DML parts, and it is, quite simply, the language of data, period. Okay, so you've got the right tools. You know the language, but that's only half the battle. You can't just throw data into tables and hope for the best. The design of your database is absolutely critical. It affects performance, data integrity, and, believe me, your own sanity down the line. So let me ask you this. Just because your data is sitting nicely in a table, does that mean it's well organized? The answer, probably not surprising, is a huge no. There are good designs and there are very, very bad ones. Take a look at this design. Just look at it for a second. Do you see the problem here? For every single instructor in the computer science department, we're storing the building number and the budget. The exact same information, 101 and $1 million, is repeated over and over and over again. This is called data redundancy, and it is a huge problem. It wastes space, and it's a nightmare for keeping things consistent. So, how do we fix this mess? Well, the solution is actually really simple, but it's incredibly powerful. You just split that one big table into two. We make one table just for the instructors and another one just for the departments. Now, the department's budget is stored in exactly one place. If it changes, you only have to update it once. This right here is the core idea of good database design. You have to eliminate redundancy. All right, we've talked about the big ideas, the language, and the design. But what's actually happening under the hood? When you send a query to a database, what's the machinery that's actually running in the background to get you your answer? Whoa, okay, this diagram looks a little intimidating, right? But all it's showing is the incredible journey your simple request takes. It's not as simple as just grabbing a file. Your query goes through this really sophisticated, multi-step process inside the database engine before any data ever comes back to you. Let's simplify this a bit. So, let's trace the life of a query. It's basically a three-step dance. First, the parser and translator figure out what on earth you're actually asking for. Second, and this part is pure magic, the optimizer determines the absolute fastest possible way to execute your request. I mean, there could be dozens of ways to get the same data, and its job is to find the best one. Finally, the evaluation engine takes that optimized plan, goes and gets the data, and sends the result back to you. So there you have it. We've talked about abstraction, schemas, languages, and design. You now have the foundational blueprint for how databases actually think and work. The only question left is, with this power to structure and manage information, what problems will you solve? What are you going to build?